Organic Chemistry, Lecture 6, Aldehydes and Ketones. What constitutes an aldehyde or a ketone? A ketone has two alkyl groups bonded to a carbonyl. An aldehyde has one alkyl group and one hydrogen bonded to a carbonyl. So, a ketone structure is going to look something like this. An aldehyde, on the other hand, is going to look something like that. Now, because of the way aldehydes are oriented, generally they're going to be a terminal group. In terms of nomenclature, you just take the aldehyde and replace the E ending on the parent alkane and replace it with an al. So, for example, if you've got butane and it becomes an aldehyde, you just simply change it to butanal. Ketones are the same, except you replace the E ending of parent alkanes with -one. So, going back to the butane example, that would become butanone. Take note that for longer chains, you have to number where the carbonyl is in the chain. Physical properties of aldehydes and ketones. There is a dipole moment that is observed in both of these, and they generally act as electrophiles. Because of this, they are common attacks for nucleophiles during things such as nucleophilic addition reactions. Usually, a nucleophilic attack of a carbonyl is going to result in the formation of an alcohol. So if I've got my carbonyl here, you're going to see a dipole moment like so, making this site a very favorable target for something such as a nucleophile. Before we talk about reactions any further, let's go ahead and talk about reaction principles, starting with the acidity of the alpha hydrogens. Alpha hydrogens are hydrogens adjacent to the carbonyl carbon. So if I were to draw out just a standard ketone, there would be hydrogens on this carbon and the next one. So for example, this is a very simple ketone. But all of these hydrogens that I've just drawn count as alpha hydrogens. The acidity of these are going to be dependent on the stability of the general structure. So how well the structure can resonate the electric charge. The removal of these is going to form carbocations because there's going to be net positives running around. The carbanion is then stabilized by the carbonyl. Steric hindrance basically states that additional groups, generally alkyl, will cause difficulty in reactions, so there's going to be stuff in the way. An example of this would be if I were to look at these two structures. Comparing this structure to a much bigger structure with a lot of functional groups, for example like so, is going to make it very difficult for reactions to occur at the carbonyl. As you can see, there is a clearer path going straight into the carbonyl here. However, because of this bulky functional group, it's going to be much harder to get to the carbonyl. Think of steric hindrance as simply saying that there's stuff in the way that stops the reaction from occurring. So we've gone over the fundamentals of aldehydes and ketones, or simply carbonyls. So we're going to go into some reactions now. Note that before we start going into reactions, most of them are going to occur via nucleophilic addition reaction of some sort, the mechanism for which is listed below. Quite simply, it is a nucleophile attacking a carbonyl and creating an alcohol because of it, which is noted like so. Because of the net dipole, which I will draw here, there's going to be a positive dipole moment at the bottom, this carbon right here, which allows this nucleophile to attack. The attack of this nucleophile is going to cause the electrons to bump up to the oxygen, which is then going to take protons from the environment and create an alcohol. The simplest nucleophile attack that you're generally going to see is via water. This is called hydration, and it's listed below. When you put a carbonyl compound into water, you will see reactions of this sort. Note that the arrows in these reaction mechanisms are denoting where the electrons will go. This results in the form of a geminal diol. So, pardon the spelling error here. It is a geminal diol. Acetals and hemiacetals. This forms depending on whether or not the starting compound was an aldehyde or a ketone. Acetals will form from attacks of compounds, ROH, so some R group attached to an OH, so some form of an alcohol, attacking a ketone. This will lead to the formation of a hemiacetal and eventually an acetal proper. Ketones will form ketals. This is also from an alcohol attack, and they will go from a hemiketal to a full-blown ketal. As you can see, hydroxyl groups and the oxygen groups that start on the chain will eventually be kicked off as the reaction proceeds. Imines and enamines are nitrogen-based compounds. An imine is a compound with a nitrogen double bonded to a carbon, and an enamine contains both a nitrogen group and a double bond. A mechanism for the formation of an imine is listed below. Note that, just like the ones we've seen previously, it is based on a nucleophilic attack of a carbonyl. Cyanohydrins are simply a compound that results from a cyanide attack on a carbonyl. You will note that there has to be a source of protons for this to continue on. So, as you would guess, something that is lightly acidic is going to help this reaction proceed. Oxidation of aldehydes. This results in the formation of carboxylic acids. Note that it does require a stronger oxidizing agent, and that makes PCC an unsuitable candidate. If you remember from our previous lecture, you'll remember that PCC is not strong enough to oxidize carbonyls or alcohols to completion. So when you want to make a aldehyde, if you want to oxidize an aldehyde, you're going to have to take note that you're going to need a much stronger oxidizing agent than PCC. Examples of these compounds are listed below. Of note, these two are the ones that you're likely going to see on your test. Oxidization in terms of the organic chemistry portion can generally be summarized as the adding of oxygens to a structure, but remember that it has to do with the loss of electrons. Conversely, we have reductions. Of the reducing agents, the ones that you'll generally see are lithium aluminum hydride and sodium borohydrate. These are the most common. The only thing you're really going to have to remember for this, though, is that sodium borohydrate is a far milder reagent than lithium aluminum hydride. For the next portion of the lecture, we're going to talk about enolate chemistry. And we're going to have to start with what an enolate is. An enol results when you shift between the keto and the enol forms. So a keto form is the one that you're generally going to see with the carbonyl. This is more thermodynamically favored. But occasionally, you're going to shift to the enol form, which is an alcohol on an alkene. Because of this shift, you're going to see various reactions occur. Take note that in general, the keto form is going to be favored. So, although this arrow is written as equivalent, it's more like this. The first enolate reaction we're going to go into is the Michael addition. The Michael addition is simply the synthesis of more lengthy compounds, and it results from an attack from another enolate compound onto an enol. So as you can see, you're going to see a passing of electrons in the presence of a base, which leads to two possible resonance structures. Of the resonance structures, eventually one of these are going to get kicked off and result in some form of an attack. As you can see, the electrons will bounce. In an attempt to stabilize, it's going to continue on, taking hydrogens off of its environment and eventually structuring itself out to look like so. Note that this reaction can continue arguably indefinitely. There are two types of enolates that are possible: kinetic and thermodynamic. The thermodynamic form is more stable, but it forms slower, and the kinetic form is less stable, but forms faster, and the condition is going to determine which one is favored. In lower temperature and strongly steric hindered bases, the kinetic form is going to be favored. However, the thermodynamic form is going to be favored at higher temperatures and with weaker, smaller bases. Examples of kinetic and thermodynamic enolates are listed below. Think about which one is going to have more resonance stabilization. Enamines are similar in a sense that they are a tautomerization between enamine and imine forms, much like enols. Imine form is generally more thermodynamically favored though. And again, it's largely just because of where the double bond is. One of the last things we're going to talk about in this lecture is aldol condensation. Aldol condensations are very similar to what we saw in the Michael reaction, but it's the synthesis of aldols from carbonyl compounds. You'll note that this occurs because an enol forms, allowing for an attack onto another carbonyl carbon. Eventually, this results in the formation of an aldol. And with an additional proton, you will get something that looks like this. Obviously, if you can go in one direction, you can go in the other as well, which is where the retroaldol reaction comes into play. This one's a lot simpler to conceptualize than the aldol condensation. Just note that you're taking an aldol and breaking it into two pieces. So, in a sense, if you look at it, you're basically splitting it right down the middle, protonating this end, and just taking this carbon off. So that will cover our discussion of aldehydes and ketones. Take note that a good understanding of these reactions will serve you well on test day. Please join us in the next lecture as we talk about a more complicated form of carbonyl carbon, carboxylic acids.